Okay, so hopefully you can hear me, hopefully you can see me pretty well, and hopefully everything's in sync. But I am going to show you today how to multiply and factor polynomial expressions, okay? So this is the first lesson that I'm going to do for Algebra 1. So what we want to do down here is write expressions for the areas of the two rectangles in the figures below. So if you remember from previous years, area is equal to length times width, okay? And if this is the case, then, right, I like to call our longer side the length and our shorter side the width. So in this case, my length is 2z and my width is z. Well, if I multiply those two in this case, the area of the small rectangle is going to be 2z times z, which is equal to 2z squared. All right? And then if you take a look at this one, right, my length, my longer side, and as at least how it's looking, is the 8, okay? So if that's my longer side, then 2z is my shorter side. So 8 times 2z, my area is equal to length times width, which is 8 times 2z, which is equal to 16z, okay? So then in mathematics, we're saying, okay, what happens when you put the two together? Well, think about this. I've got z length over here, and then 2z width over here, and then another 8 length. So I'm adding 8 to z, okay? So this is like distributing 2z to each portion. So I'm adding 8 units to the length of z. And if that's the case, then, well, I can just write area is equal to length times width, which my length is z plus 8 times 2z. And anytime you can write two expressions like this, you can use the commutative property of multiplication and just switch them around, and then 2z can distribute. So if that's the case, I get 2z squared plus 8z. And we're done. Well, down here, the area of a rectangle in square units is represented by 3a squared plus 3a for some real number a. So find the length and width of the rectangle. How many possible answers are there for Jack's challenge to his friend? List the answers you find. So there's a few possibilities, but this is where we decide what GCF is. So if you think about it, that a has been distributed to both terms. Just like up here, right? You saw that z was distributed, and we got, when I distributed 2z, I got 2z squared plus, and that's not 8, it's my mistake, 16z. Okay? So, if you think about it, this a has been distributed to both terms, but not only the a has been distributed, but also the 3. So if I think about it, I could split this up, and I could call this side 3a, oh, maybe make it the longer side. So maybe this is the side. So this is 3a. And then this side is a plus 1. And so this works, right? If my length is 3a and my width is a plus 1, well, that just means that 3a times a plus 1, my 3a is going to distribute, and I get 3a squared plus 3a. And that's it. That's all I have to do for that. And then, so they said, see and list how many answers you can find. Well, right, you could have said that 3 was the only factor, and one side length is a squared plus a. Or you could have said that a is the only factor, and then 3a plus 3 is the width. So there are multiple ways you could have written this. So, right, if this is the width, so this is the width down here, or maybe the length, and then this is the width and maybe the length. So there's a few possibilities here, but this is the first place that you see that a GCF can be taken out. So in this case, the GCF is 3a. It's the highest value you can undistribute from every term. So let's talk about the GCF down here. Well, with the GCF, we want to find the highest number that all the integers, the coefficients on all these variables, are divisible by. So if you notice right here, 10 and 5 are both evenly divisible by 5. So 5 is the GCF. Both terms also have an a. So if that's the case, I can factor out an a. So I've got 5a comes out to the front, and then right here, 10 divided by 5 is 2. And then this a is undistributed, so it's like undistributing a value. So that a is factored out, comes to the front, it's no longer there. So it's just 2b, because that b has not been undistributed, plus 1. And that is fully factored. So then you could come down here and factor things like this. So 3g cubed h minus 9g squared h plus 12h. Well, now I have to break this down into components. Well, I know that each individual number is divisible by 3. So I know 3 is part of the GCF. But then I have to decide what variables I can factor out. So if I expand this out, anytime you see something to the third power, that means that it's being multiplied by itself 3 times. So g times g times g. And then h. So I have 3 g's here. And then right here I've got negative 9 g times g, h. And then I've got plus 12h. So it's almost like I'm playing a matching game, right? Every single number is divisible by 3. So I'm actually going to split these factors into their factored form based on factoring them by 3. So 9 is divisible by 3, it's 3 times 3. And then over here, 12 is divisible by 3, and that gives me 3 times 4. So this is not 33, it's multiplication, so make sure you understand that. And then h is left. Okay? So if you take a look here, change my color here. You take a look here, I'm trying to see what they have in common. So every term does not have a g. So g is not part of the GCF. A variable is only a GCF if it's in every term. And you take the highest amount that you can. So right here, if this term over here had a g, then it would be a GCF. But notice that every term has an h. And it's h to the first power. So anytime you see just one letter, it's to the first power. Okay? So since every term has an h and every term has a 3, that can be factored out. So what I do is I write that 3 at the front as well as h. And I'm left with, change my color back. I'm left with g cubed. So g cubed is still there. Minus, and I only took 1 3 out of this term, so I'm left with 3g squared h. And then over here, I factored out a 3, so I'm left with plus 4h. And that's it. So let's do another one here. So each term has so this term has x squared, y cubed, and this term has x y to the 4th, and this term has y to the 5th. So not every term has an x, but every term has at least a y. So if I think about expanding this, and also write every term is divisible by at least 3, so I take a look here and I ask myself, can I divide 9 by 6? Is that a larger number I can divide by? And the answer is no. So the highest number I can divide each one of these terms by is 3. So I'm going to split these up. So I've got 3 times 2, and I'm not saying you have to do this for every single one. If you see the GCF, that's good. But if you don't, this may be helpful to you. So 3 times 2 is there, and then I've got 2 x's and 3 y's for that first term. That's what this is equal to. And then plus 9x and then 4 y's. Now it's important to notice and note, so this is something you probably should put in your notes. If you see a 4 beside a y, that means you have to write out the y 4 times, okay? So this 4 only modifies the thing immediately to the left unless there's parentheses around these items down here. So as a side note, right? If you see the 4 on y, that means y is being multiplied by itself. But if I had a quantity like x times y to the 4th, that means x times y would be multiplied by itself 4 times. So this is equal to x, 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 y, 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 all multiplied, okay? So be careful. Unless a power is on the outside of the parentheses, it's only modifying the thing immediately to the left, okay? And then 9, I forgot to do that, so let me fix that. Got rid of him. So 3 times 3 is 9. I'm going to put that in there. That looks awful, so I'll put it up here. And then lastly, right, 18 is divisible by 3. So that's 6 times 3. And then I've got 5 y's here and no x's. So if I take a look at all these values, I have 3 y's here, 3 y's here, and 3 y's here. Y cubed is in every single term. It's just hidden in it. But x, since I've got 2 here and 1 here and then none here, I can't factor that out. It has to be in every term to be factored out. But this 3 matches in every single term. So I can factor him out to the front. So I've got 3 y cubed comes factored out. And then the rest of the stuff just goes inside the parentheses. So 2 is left. So I'm going to kind of cross some of this stuff out. And I'm not saying it's canceling. I'm just saying we factored it out to the front of the expression. So, yeah, 2x squared, and then one of these 3's is canceled, so I've got plus 3xy, that's not division, plus 3xy, plus 6y squared. And that's it. That's all we have to do for this expression. It's fully factored. There's nothing else that can be factored out of this, and we're done. So some things to talk about. Prime number definition. A prime number is a positive integer greater than 1 whose only positive integers factors are 1 in itself. Okay? So if there's nothing else to factor out, then if 1 is the only GCF, then there really isn't a GCF. You don't have to write that outside. Composite number. A composite number is a positive integer greater than 1 that is not a prime number. A composite number can be written as the product of positive integers with at least one factor that is not 1 or itself. For example, the prime number 7 has only 1 and 7 as its factors. The composite number 6 has factors of 1 and 6, 2 and 3. It can be written as the product of 2 times 3. So a composite number is basically not a prime number. It's an integer that is divisible by another integer. A non-zero polynomial expression, so a polynomial, we'll get to that term, with the integer coefficients is said to be prime or irreducible over the integers if it satisfies 2 conditions. So we're talking about polynomials that are prime. 1, it is not equivalent to 1 or negative 1. And if the polynomial is written as a product of 2 polynomial factors, each with integer coefficients, then one of the 2 factors must be 1 or negative 1. Given a polynomial in standard form with integer coefficients, let C be the greatest common factor of all the coefficients. The polynomial is factored completely over the integers when it is written of a product of C and 1 or more prime polynomial factors, each with integer coefficients. So using a table as an aid. So you may have seen the geometric area model used in previous examples to demonstrate the multiplication of polynomial expressions for which each expression was known to represent a measurement of length. Without a context such as length, we cannot be certain that a polynomial expression represents a positive quantity. Therefore, an area model is not directly applicable to all polynomial multiplication problems. However, a table can be used in a similar fashion to identify each partial product as we multiply polynomial expressions. The table serves to remind us of the area model even though it does not represent area. So as an example, we're going to try and multiply and do partial products of x plus 2 times x plus 5, then write the product of x plus 2 times x plus 5 in standard form. So I'm going to do this 2 ways. I'm going to do exactly what I said. X times x is x squared. X times 5 is 5x. x times 2 is 2x. So I'm multiplying each row by each column. So x times x here is the first two. X times 5 is the next two. And then x times 2 goes in this box, and then 5 times 2 goes in this box. So then I can add things up. So I only add along the diagonals because those are the only ones that have like terms. So over here I've got x squared. And then over here I've got 7x. And then over here I've got 10. And that's it. That's all this quadratic is. So this is a binomial times a binomial, which becomes a trinomial, right? So leading coefficient, a leading term is to the second power, second term is to the first power, and then the third term is constant. That's a trinomial, or it's also known as a quadratic, okay? So there's another way I can multiply these. I can take x plus 2 times x plus 5 and then distribute this stuff out. So x times x and x times 5, 2 times x and 2 times 5. So I've got x squared plus 5x plus 2x plus 10, okay? So then I can combine these two like terms, and this is the exact same thing, just a different way of doing it, okay? So this is just a rewrite of the distributive property, and dare I say it, it's called FOIL, okay? So I'm not saying this is exactly FOIL, I'm saying that that's a good acronym to remember how to multiply a binomial times a binomial. So this acronym is only applicable to a binomial times a binomial. Oh no, my daughter's giving us fits. Okay. So here's a good table to talk about, regardless of whether or not we make use of a table as an aid. The multiplying of two binomials is an application of the distributive property. Yeah, so you're distributing x to both terms, and then you're distributing y to both terms. So this is the first two terms being multiplied. This is the outside terms being multiplied. This is the inside terms being multiplied, so x times y. And then the last two terms, so negative 5y. And this is how it's written. So first terms, that's what FOIL means, first. Outside terms being multiplied, I, inside terms. And then L, last terms. So f goes with x squared, x times x, that yellow color. Green color, x times negative 5, so negative 5x. Orange color, y times x, so plus yx or xy. You can write it either way. By convention, we like to switch those. So write the variables in alphabetical order whenever they're being multiplied. And then y times negative 5, so negative 5y there. So here's our next example. We're talking about the difference of squares. So find the product of x plus 2 in parentheses times x minus 2. Use the distributive property to distribute the first binomial over the second. So this right here is called a binomial. So we talked about that. So it's two terms. The first variable has a power of 1, so does the second variable. So when I multiply these out, x times x gives me x squared. But x times negative 2x, and then, yeah, so this table does a good job of explaining it, but I'll explain it as well with the FOIL thing we've got going on. So the distributive property. And remember, this only works with two numbers by two numbers. So if you have 3 terms over here, 3 terms over here, or 4 terms over here, 5 terms over here, or 1 term over here, FOIL will not work. Or that acronym will not help you out very much. You'd have to distribute the values to each part. So they're saying x times x is x squared. X times 2 is 2x. Negative 2 times x is negative 2x. Negative 2 times 2 is negative 4. But if I add across these diagonals, the b term of your trinomial, your 2x and your negative 2x, your linear term will cancel out. 2x minus 2x is 0. So x times x is x squared, and then 2 times negative 2 is negative 4. So x squared minus 4. Same thing here. X times x is x squared, so this is just the same thing. X times 2 is 2, and that should be a minus 2. Yeah, plus 2x. X times 2 is x times negative 2, my bad. X times negative 2 is negative 2x. 2 times x is positive 2x. And then 2 times negative 2 is negative 4. Okay? So this is equal to negative 2x, and 2x will add to be 0. So I've got x squared minus 4 is left. And so by the use of the table, they're showing all those steps out, and it's the same thing. So that result that we talked about, and here's another way of writing it. Let's see if I can do it. A squared minus b squared, right? Anytime I have some quantity squared minus some quantity squared, it can be factored easily as a plus b times a minus b. So you take the square root of the first two terms and then place them in their correct positions. So let's try it out with this guy. T squared minus 25 becomes t plus 5 and t minus 5. So the square root of t squared is t, so t goes there and there. Square root of 25 is 5, so that goes there and there, plus and minus. So these two things are equal and they're fully factored. So similarly down here, 4x squared minus 9, whenever I factor this out, I'm left with 4x squared, the square root of 4 is 2, square root of x squared is x in this case, so 2x plus square root of 9 is 3, and then the second term will be 2x, square root of 9 is 3, so negative 3. So if I foil or distribute all this out, you will find that these two things are the same. So I'll show that here in a second. Yeah, I'll go ahead and show that now. So write 2x times 2x, 2x times negative 3, 3 times 2x, and then 3 times negative 3. So 2x times 2x is 4x squared. 2x times negative 3 is negative 6x. 3 times 2x is positive 6x. And then 3 times negative 3 is negative 9. So these two things cancel out, and I'm left with 4x squared minus 9. And that's it. That's the same as what we had over here, okay? So now we're on this one, and it's the same song and dance, right? All you have to do is take the square root of the first two terms and the square root of the last two terms. So the square root of 16 is 4, and the variables matter here. The square root of h squared is h. So 4h and 4h here, plus, minus, square root of 36 is 6, square root of k squared is k, so 6k and 6k. 4 minus b squared, I've got 2 plus b, and then 2 minus b. So square root of 4 is 2, so that goes there and there. Square root of b squared is b and negative b. So it works all the same out. So here we go. Let's do some harder ones. So x to the fourth minus 4. Well, that becomes square root of x to the fourth. Whenever you take the square root of a power and the power is higher than 2, you're essentially dividing it by 2, okay? So square root divides powers. So 4 divided by 2 is 2. So in my parentheses, x to the fourth becomes x squared whenever I take the square root of it. And then the square root of 4 is 2. So plus 2 minus 2. And then down here, it's really similar. So down here, 6 divided by 2 would be 3. So I'd get x cubed and x cubed here. So 25 becomes 5 and negative 5. And then here's the general formula, a squared minus b squared. We want to find this in factored form. And this is exactly what we were doing the entire time. It's just a rewrite of some of the other things. So the square root of a squared is a. And then the square root of b squared is b. So a plus b, a minus b. So that's the general formula. And then here's some more stuff. So this is getting monotonous at this point, but we can go ahead and do it. 9y squared. The square root of 9y squared is 3y. The square root of 100z is 10z, so this will be plus 10z. And then 3y minus 10z. Okay, same thing down here. Well, that's right. Okay. A squared, square root of a to the fourth is a squared, square root of b to the sixth is b cubed. Right? 6 divided by 2 is 3, 4 divided by 2 is 2, and then over here, a squared minus b cubed, same thing. So we're just applying that formula. And it says, okay, hint, this one factors twice, you gotta continue to factor. Oh, this is freaking fantastic. R squared, square root of 16 is 4. Square root of s to the fourth is s squared. Okay? And then r squared, and it's not going to be plus, it's going to be minus. That was a mistake. Minus 4s squared. Okay? So actually, this is false. I won't go into it in this lesson. You can go on and figure that out in Algebra 2, but this does not only factor twice, this factors thrice. This can actually factor if you believe in imaginary things. But okay, anyway. Square root of r squared is r, square root of 4 is 2, so square root of s is s. S squared is s, yeah. So r plus 2s, r minus 2s. So that's the thing it's talking about. So if you take a look at this and it's also a difference of squares, you can factor it further. And that's it. So anytime you see a binomial with a square on the outside, you need to be careful when you use the distributive property too often. This too, a lot of students will say that x plus 3 squared is equal to x squared plus 3 squared. This is not true, okay? And we can show that, but whenever you square something, you're telling yourself to multiply this item by itself, okay? So when I take x plus 3, I'm taking x plus 3 and multiplying it by itself. And whenever I do that, I can use even FOIL here, or the distributive property. So x times x is x squared, x times 3 is x times 3, 3 times x is 3 times x, and then 3 times 3 is 3 times 3. And then x squared here plus 3x plus 3x plus 9, that's just some bookkeeping from this step. And then you combine like terms, so 3x plus 3x is 6x. Okay, so moral of the story is you cannot distribute a 2. So whenever you see something like x plus 5, resist the temptation of taking the 2 and placing it on top of each of these terms. This is not how it works. Okay? And we showed why. If you plug in some values, it doesn't work that way. Okay? So down here, a plus b quantity squared is what we're dealing with. So whenever I write a plus b twice, I'm going to distribute the a to both of these terms and then the b to both of these terms. So a times a is a squared. A times b is ab. B times a is ab. And then b times b is b squared. So if I have a squared plus 2ab plus b squared, what I've just done is these are general examples to determine the general rule for squaring a binomial, okay? So if you have two values inside these parentheses, a plus b squared, then this formula holds true. I can take a plus b, square it, and it's equal to this every single time. So as an example, I don't even have to FOIL it out if I know that, or distribute it out if I know that identity. My a term is 3x. My b term is 5. So I can go ahead and write this out with a squared plus 2ab plus b squared. So 3x times 3x is 9x squared. Sorry about my daughter. She's just in a bad mood. She's in a funk. She's being a little hateful. So, right. Okay. So the next step is plus 2, and then I'm going to multiply a and b together. So a is 3x and b is 5. So 3x times 5 is 15x. And then 5 times 5 is 25. And that's it. So down here, something similar. We've got a minus b squared, and this is equal to a minus b times a minus b. Well, this is equal to a squared minus ab. So a times a is a squared, negative ab, negative ba, which is the same thing as negative ab. So there it is again. Negative b times negative b is negative b squared. Okay? So a squared minus 2ab. Oh, negative b times negative b is positive b squared. That was my bad. Plus b squared. Okay? And that's it. So all this is saying is if you have two quantities, like earlier, instead of 3x plus 5, I'll do 3x minus 5. If I had 3x minus 5 squared, it would equal 3x quantity squared, so 9x squared, right? 3 squared is 9, x squared is x. I mean, x squared is x squared. And then 3 times 5 is going to be negative 2 times 3x times 5, so 15x. And then b squared will be negative 5 times negative 5, which is just 25. So these identities make it quicker to deal with certain things as long as you can remember the formulas. Okay? So down here, they're asking you to square the binomial using that fact. Well, that's just going to be, right? A squared plus 2ab plus b squared is our formula. So a squared is a squared. 2ab is going to be 2 times 6, which is 12, 12a. And then 6 squared is just 36. So we're using these formulas. And then same thing here. If I just regurgitate that formula, I can actually do this easy. So 5 squared is 25. 5 times w is 10. Yeah, 5 times w times 2 is going to be negative 10w. And then negative w times negative w is going to be w squared. So negative w squared is w squared. So that's it. That's all you have to do. You can just use the formula. So these are the 3 formulas that are going to be helpful. And so let's see. If you need for homework, suggest definitely these. Yeah, all these. If you need some practice.